Welcome back, guys. Today we are looking at really the final piece to the genetics puzzle, and that is looking at how we sort and solve pedigrees. So we're going to be sketching out 4 different pedigrees and talking about how we go about solving them, finding those inheritance patterns, and deriving from them some meaning. So today we're looking at pedigree analysis. Pedigree analysis. And a pedigree is simply a chart that is going to illustrate genetic inheritance over multiple generations. So we'll say a chart that illustrates genetic inheritance patterns, because really there's patterns we're looking for over generations. So there's 4 different varieties, and we're going to work through those 4. So the first one that we're going to look at is what we call autosomal, and it's going to be recessive. So this is a pedigree. What we're looking at right here, this is a pedigree. And you can see that there's generations on the side, 1, 2, 3, 4 in Roman numerals, and then everybody else in the pedigree is numbered. And that is so we can identify individuals. For example, if we're talking about an individual here, we'd say generation 2, 4, and we could refer to this person. Females are represented by circles and males are represented by squares. And then some trait or disease is depicted with a shaded individual. So if the individual is shaded, that means they have this trait or this disorder that we're tracking throughout these generations. So this is the general setup. We're talking about, in this first type of pedigree analysis, autosomal. And what an autosome is one of the 22 chromosomes that are non-sex chromosomes. So if something is autosomal, it's on one of these 22 pairs of chromosomes. It's not on the sex or the X chromosome. So if we go back to our notes here that we're writing, an autosomal recessive pedigree is going to be one where we see traits. So we'll say a trait may skip a generation. So the trait may skip a generation, and we're going to look and see what exactly that means. We've got this term autosome up here, so let's remember that this means that it's on a body chromosome. So on a body, B-O-D-Y, chromosome, or an autosome, that's numbers 1 through 22. And again, each person in the pedigree, will have or has 2 alleles for each trait. So this means if it's on an autosome, each person is going to have 2 alleles for each trait. So they're going to get 2 letters assigned to their genotype. Again, we'll draw what this means. If a trait is skipping a generation, what we're looking for is 2 unshaded individuals having shaded offspring. That's kind of the giveaway you're looking for. So if we go to this pedigree, back to this pedigree, here's that instance. 2 unshaded offspring, individuals in generation 2, 1 and 2, they're unshaded, yet they're having shaded offspring, individual Roman numeral 3, 2. So this piece right here would tell us that this is inherited in a recessive fashion. Okay, the fact that we have 2 unshaded offspring having shaded off, or 2 unshaded individuals having shaded offspring. So what you might be asked to do is draw a pedigree. for some particular trait. So I'm just going to sketch a simple one out. So squares are going to represent males, circles females. We draw a link between them to show that they're a breeding pair. And then their offspring are going to be located on this line. So let's say that they have a son, they have a daughter, they have another son, they have another daughter, and then they have another daughter. And more data typically is better in terms of figuring out these patterns. So let's say she marries somebody here, and then this gentleman marries somebody here. So we have generation 1, we have generation 2, and then we'll just go to a third generation here, generation 3. I'm going to drop down. And we'll say that we'll say we have a son, and then 2 daughters. So a son, daughter, something like that. And we're going to go ahead and shade some of these individuals. So let's say, and again, I'm just doing this somewhat arbitrarily and random, not necessarily random. I have a point to this. But we're going to try to highlight what you would see if it was a recessive autosomal type of inheritance pattern. So this might be what you have. And in this case, here is what we're looking for. 2 unshaded individuals having shaded offspring. That's this right here. So this would tell us it's recessive. Now, we haven't gotten into what do we look for if it's X-linked, but for now, let's say it's recessive. So the shaded allele is going to be the recessive allele. So this is going to be the shaded or the affected individuals. And then the big A will be your normal alleles. Now, because this trait is carried on autosomes, chromosomes 1 through 22, each person is going to have 2 alleles. Right, and it goes back to this idea here that, again, each person has 2 chromosomes, 2 autosomes, so you would have a letter on one chromosome and a letter on the other. Which means we're going to start with these shaded individuals, and we're going to assign all of them 2 lowercase letters that represent the 2 recessive alleles, like that. So that's the first thing we're doing. We're assigning genotypes. Then what we're going to do is we're going to start figuring out the other genotypes. So if this person ended up with 2 little a's, one of them came from mom, the other one must have come from dad, and he's not shaded, which means he must have a dominant allele here. Also, we see that if mom has both alleles, every one of these kids will get one as well, and they're not shaded, so that means they must have a capital A there as well. So that's how we go about assigning genotypes. Again, we have the same thing happening down here, where we have 2 little a's, so little a must have been provided in this case. Over here, the same thing. Actually, not the same thing. We don't know what this person is. So we would just put an underscore there because we're not sure. They could be big A, or big A, little a, because we don't have any evidence really, other than they don't have the trait. So we're going to then leave these people with an underscore as well, because it could be big A, or big A, little a. Again, we could calculate those odds, but we don't know for sure, so we just leave them like that. Okay, same thing here. Right, because these could be big A, or big A, little a. Where that's coming from is, think of a Punnett square. So we'll just work a quick Punnett square here with the parents from up here. So big A, little a, big A, little a, big A, big A, little a, big A, little a. We know they're not little a, these people, because they're not shaded. So there's really a 33, a 1 in 3% chance that they're big A, and a 66, 2 in 3 chance that they're big A, little a. But we just leave them there because we don't know for sure. Next thing we're going to look at is the next progression, and that's going to be autosomal dominant traits. So autosomal dominant. And what we look for in this instance is we look for the trait in every generation. So the trait typically is in every generation. So it doesn't skip a generation. So we're not skipping a generation. Now, occasionally, what you might see is you could look for two shaded individuals. So two shaded parents have non-shaded offspring. So that's one thing we might see in a pedigree, and we'll pull one up and get a look at it, and then we'll go ahead and sketch one as well. So looking at this pedigree here, again, we said this was a recessive pedigree. So again, we're skipping generations on this left side, and we're skipping generations in the middle here. So if this was shaded, if number 2 here was shaded, number 3 here was shaded, that would be more reflective of a dominant type of inheritance pattern, where it will be in every generation. So we're probably going to need to sketch this one, because this example here is an example of recessive inheritance. We want to look at dominance now. So we're going to go ahead and do that. And again, this is on an autosome. So each person is going to have 2 alleles. So I'm going to start with my initial couple here. This is generation 1. I'm going to draw my generation 2. So we'll put a couple of males and females in Gen 2. This is generation 2. And then we will marry this person, or just breed those 2 people. Don't have to necessarily marry them, I guess. And this is now a generation 3. We're going to say, put 4 people here, 2 boys, 2 girls. We'll do the same thing over here. Again, the ordering is not really important. And then we're going to shade it to reflect a dominant inheritance pattern. All right, so let's say we've got one here, got one here, got one here, got 2 here. And then we've got these 2 here. So first thing we look at is that it's in every generation over here on the right. So it's in every generation. We're not skipping a generation. Then over here on the left, this is that situation also where if it's not in every generation here we haven't skipped a generation, but we just don't have one here. So maybe if these individuals had offspring, maybe it does skip a generation. But what we then would see is 2 shaded parents have non-shaded offspring. So the trait, again, is being masked by a dominant allele, in which case we would say that the big A is the modified version, which is producing the shaded phenotype in this case. And then the little a is the more normal, what we're not considering the trait in this case. So in this one, we would go around and we would start identifying all the individuals that are not shaded. They would have both recessive alleles, because if they didn't, they would have a big A and be shaded. So these guys are very easy to knock out, because if they had a big A, they'd be shaded. So that makes us then just look at the people that are shaded. And again, this guy here is going to get a little a from mom, and he's shaded, so he's got to have a big A. Same thing here, and same thing over here. We're passing on 2 little a's to this daughter, which means dad has got to provide one, and he's shaded, so he's going to have a big A. And then we're left with just a couple of people over here. We've got to have a little a and shaded, so it's got to be big A, little a. And then over here, again, little a from mom, we're shaded, so it's big A and it's big A. So that's how you go about sorting this. Now, there might be a question where we ask, what are the odds all four offspring here are unshaded, right? All four offspring here are unshaded. That seems like that'd be pretty rare if both parents had the dominant allele, right? And when you think of this, when you think of a Punnett square like this, right, this little a ends up 1 out of 4 times. So you'd have 1/4 for this kid, 1/4 for this kid, 1/4 for this kid, and 1/4 for this kid. So you would have to multiply all those odds and you would get 1 out of 256 would be the odds that all four offspring are unshaded. So pretty unlikely that we would see the pedigree set up like this. 1 out of 256 would be the odds. You would expect really one of these individuals to be shaded, but that can occur. It's possible, but it's quite rare. Right, the third variety that we're going to look at here is sex-linked, just like the Punnett squares that we did, or X-linked, because it's on the X chromosome, and we're going to look at recessive pedigrees first. And what we're looking for with these is going to be a trait. So the trait may still skip a generation, but this time we're going to see more males that are affected because they just have one X chromosome. So there's no chance that a recessive allele can be masked. So it's always going to be expressed if it's there. So more males affected. And if you have an affected female with both recessive alleles, they're going to have males that are affected 100% of the time. So affected females must have all affected sons. So let's go ahead and look at this pedigree and see what we have. Again, it's recessive, so we know it's recessive because we're skipping a generation. Do we have a disproportionate and unequal number of males and females? We've got 3, 4, 5, 6, 7 males, 1, 2, 3, 4, 5 females. So slightly, let's look and see if we have an affected female. She's got to have all affected sons. She doesn't, right? This female doesn't have a shaded son. So we know that this is not being X-linked. We know that this would be recessive. So let's draw one that is X-linked. So again, it's on the X chromosome. So let's go ahead and sketch this out. So we got a male and a female. That's gen 1. Here's my generation 2. And let's say in generation 2, I have a daughter, another daughter, a son, a daughter, and another son. Then I breed these two people here on the ends. Then I make my generation 3. So this is gen 3. And I'm going to have a couple of males in this generation and a couple of females. Same thing over here. And then let's say the shading pattern was this. So we had a shaded male in gen 1. We had a shaded female in gen 2. 2 shaded males here. And then a shaded male like over here. So we have 1, 2, 3, 4 males versus 1 female. So we have a disproportionate number of males and females. Again, it's a small sample size here. And we have a shaded female having all shaded sons. So those are some things that we would look at. So in this case, the males have just 1 X chromosome and the females have 2. It's recessive. So we would say that the lowercase a is the shading. The capital A then is the normal allele. And this would be something like red-green color blindness would be inherited in this fashion. So an example of this would be like red-green color blindness. And what we would say then, or what we would start seeing, is we would start with the males. So we'd have an X with a little a, and then we'd have to show that Y chromosome because they only have 1 X chromosome. This male here is the same. This male here is the same. Again, if they had a big A, they wouldn't be shaded. So all the males that are shaded have the same genotypes. All the males that are unshaded, they have a big A on their X chromosome. So males are really easy to sort out because if they're shaded, they're one way. If they're unshaded, they're the other way. There's no carriers. So you don't have a lot of options when it comes to assigning male genotypes. Now the female is a little more tricky. We can start with this female here. She's got to pass on the recessive allele to these sons and the dominant allele to these daughters. So she's going to be heterozygous. She's going to have both. Actually, strike that. Strike that. The daughters, it's X-linked, so the daughters are actually getting the dominant allele here from dad. So we would say that, and she's shaded, so we know she's got both recessive alleles. That makes way more sense. So she's got both recessive alleles, meaning she's passing 1 on here to the sons. To the daughters, she's passing 1 on as well, but they're getting the dominant allele from dad. So they're going to be heterozygous and carriers. Over here, so dad is passing on the little a. Here, they're not shaded, so they've got to be X big A, X little a. Again, they're getting a big A from mom, getting a little a from dad. Mom here has to be able to pass on a little a. So mom has to be able to pass on a little a, as does dad. So we know that this individual is heterozygous. Again, it just takes practice doing these to really get proficient and good at them. You're not going to be good right away. We know mom here has to be somebody that is going to pass on this allele to one of the sons. We know that she's got to have both because one's got to get the dominant allele, one's going to get the recessive allele. So one's going here, one's going here. As far as the daughters go, daughters are getting a big A or a little a from mom, and then they're getting a big A. They're always getting a big A from dad, so we don't know what that other allele is they're getting from mom. So we're just going to leave it as an underscore because we don't know for sure. And that's how we would sort this pedigree out. That's what we would look at, how we would do it. Finally, to finish this up, we'll look at the last progression, and this is going to be X-linked dominant. So we're going to say sex-linked or X-linked and dominant. And with this particular trait, again, we're looking for dominant traits to be in every generation. So the trait may be in every generation. Typically we see more females affected because they're always getting a dominant allele than if dad has it. And there's 2 opportunities to get that dominant allele. And affected males will always have affected daughters. So a little bit of a different play on inheritance patterns. So that's what we're looking for. So we're going to go ahead and sketch out a pedigree and again try to illustrate these patterns for you. So again, we're going to have, let's start with a male and a female. So that's generation 1. Here's generation 2. And we're going to put a female here, another female, a male, female, and a male. We're going to then breed the 2 people on the end just to provide us some space. It's our 3rd generation, generation 3. And we'll go male here, and then we're gonna have maybe 4 daughters, change it up a little bit. Here we'll have 2 sons, keep this one kind of standard. 2 sons, 2 daughters. This is Gen 3. And let's go ahead and do a little bit of shading. So we'll say that we'll shade this one, we'll shade this one, we'll shade this one, and then we'll shade these here and these here. So we have a bunch, we have quite a few people shaded. So 1, it's in every generation. So that tells us that it's likely dominant. And then we have more females, 1, 2, 6, 7, 7 versus 2. And we have shaded males always having shaded daughters. So again, those are the talking points that we need to look for if we're talking about X linkage and being dominant. So in this case, the big A is giving us our shaded individuals. Our little a then is our more normal phenotype, or what we're considering normal. So all the normal people are going to have 2 lowercase alleles. So let's start with the males. So males here would be X with a little a and a Y, 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 right? They all have the normal phenotype. The males that are shaded then would need the big A and a letter Y. Then females that are normal are going to have 2 little a's. So we can knock those out. Again, if they had a big A, they'd be shaded, so we know they've got 2 little a's, which then leaves us with figuring out the rest of the females that are shaded. So now, let's start down here at the bottom. These females are getting at least have 1 big A, so we'll go ahead and put those there. Then mom, so they're getting that from dad. Mom is going to give them a little a, so they're all going to then have this other little a. So they're all heterozygous in this case, right? Because dad is giving the big A, mom is giving the little a. Let's go over here and look at these individuals. Again, they've got a big A because they're shaded. Mom is, though, giving a little a, so they're also big A, little a. Which leaves us with mom up top. She's got to provide a little a here. Dad's giving a little a, so she is big A, little a as well. So this is how we sort pedigrees. The only way to get good at this is just to try some. So there'll be a problem set posted probably Monday where you will go and work through some pedigrees and assign genotypes and find inheritance patterns. Okay? I hope that's helpful. I'll see you next time.